So thank you guys all for coming. My name is Alex, and this is my first Strange Loop, so I'm super excited to be here talking to you all today. I am a software engineer at a startup called Cockroach Labs, and what we're doing there is working on building an open source distributed SQL database. And I know the name is kind of silly, Cockroach Labs, the database is called CockroachDB. The idea is just that, like cockroaches, the database replicates itself and is very hard to kill. So hopefully it doesn't make anyone here a little too uncomfortable, but that's the name. I'm not here today to talk to you specifically about Cockroach, though. I'm a huge fan of databases, and I'm really interested in how this new class of databases that's been coming around the last 5 to 10 years, these distributed SQL databases, I'm interested in how they fit into the historical context of databases, why they're being built now as opposed to 20 years ago, and what makes them different from old databases or from previous databases. And so that is what we're going to take a look at today. Why a distributed SQL database? Why would anyone care about them? Why would you devote years of your life to building these things or millions of dollars to building them? And how do they work? So specifically in how they work, we'll look at how data gets spread around the system, how it gets replicated in a consistent way, and then how transactions get layered on top in this distributed computing environment. And so let's start by looking at the history. Anytime someone introduces a new system, you really need to ask why. How is this system going to be better than the hundreds of systems that have come before it in the history of computing? And why is it being built now instead of previously? What do you know now that developers before you didn't, that they weren't able to build this system instead? And so we'll begin with the very first databases. And these were being built in the early 1960s at companies like IBM and General Electric. These databases were pretty primitive because they were the first ones of their kind. They didn't know a whole lot about what they were doing yet. The interfaces that they exposed to programmers were very tough to use. So rather than having like a table of records like we're used to today or a key value interface like we're used to today, it was almost like they were programming more against an in-memory data structure. There were these series of records that your queries would have to iterate over one by one and traverse links between the records. So you might traverse from like an organization record to iterate over all of the employee records that are working at that organization. And the queries that you wrote were really tightly coupled to the storage format of the data on disk. And so if you ever wanted to change that to optimize for different access patterns, you'd have to pull all the data out of the system, load it all back in, and then to top things off, you'd have to rewrite all of your queries as a result. So this is a huge pain. They were really hard to use or required a lot of effort to use. And so this started to change in the early 70s. There was a mathematician by the name of Ted Codd at IBM who saw all of the programmers around him at IBM in his office having to spend a ton of their time rewriting these queries, optimizing the access patterns, changing the layout of data on disk, and thought that there had to be a better way. And being a mathematician, he was all about elegance. And so he created what's now known as the relational model, which powers all the SQL databases you're familiar with today. And this relational model wanted to get rid of this tight coupling between queries and how data is stored on disk. So it relies on very simple data structures, the table that you're probably familiar with, and a high-level query language, which is now known as SQL. And the queries here are very independent from the storage on disk. So the database software is free to optimize things underneath the covers without the programmer needing to worry about it. It can change how things are stored without anyone ever having to know. So these systems were much more developer-friendly. And as a note of historical context, they were always designed to just run on one machine. In the 70s, most organizations didn't even have one computer, let alone multiple computers, let alone have multiple computers that they wanted to devote to running a database. So these systems were always built for a single machine. The first commercial database was released in 1978 by Oracle, and it just kind of exploded from there. Over the next couple decades, SQL continued to mature, to grow, to gain popularity. More vendors started putting out SQL databases. There were acquisitions. There was lots of competition. It was great. But in this time, there was also a new kind of database that got introduced that didn't really take off. It was attempted, but didn't get the necessary traction. And these were object-oriented databases. The motivation for these systems was that object-oriented programming languages were growing in popularity in the 80s as well. C++, I believe Java, and there is a bit of an impedance mismatch when you're trying to translate between the objects that your program has in memory and the rows and columns that SQL databases store. So they argued that these were easier to use because you could effectively just take an object in memory and dump it into the database as a single object. It was a lot like today's document-oriented NoSQL databases. But at the time, there wasn't enough reason to switch. In order to switch, you had to give up things like complex queries that SQL databases allowed. And all these different object-oriented databases had pretty disparate APIs. There was no real standard, as there was with SQL. So these systems never quite took off. The first real big change in how databases worked or how they were used came in the early 2000s during the web boom. So suddenly, there were more and more companies that needed to support more and more users. They had to build services to support millions and millions of users, and that had to be up 24/7. And they just couldn't scale their databases to support this. You can only scale a SQL database as big as you can buy a single machine. So you had these big web-scale companies like Google, eBay, Yahoo, and Amazon, all having to deal with things like sharding their database. And what this really meant was just that they'd get 10 machines to put their data on, and they'd break their table up into chunks. So the first chunk would go on the first machine, second chunk would go on the second machine, and so on. So this all had to be done manually by a database administrator. And then for queries to work, they had to put this middleware layer in front of all these shards to translate application queries into separate queries for the separate shards. This limited what programmers could do because they couldn't really do things across shards. And any time the data grew to be too big to fit on their current number of shards, it was a huge operational headache to try and reshard, to move all the data onto different machines so that you could have more of them to account for all the growth. And so this was worth it for the really valuable services that these companies were building back then. Like Google famously sharded a MySQL setup for their AdWords product. But they realized it wasn't worth it to do this for all the little services that they were building. This might not be worth it for smaller services like Google Calendar due to all the effort involved. And so around the same time, those same companies, Google, Facebook, Amazon, all started building NoSQL databases. And these NoSQL databases had the primary goal of being scalable. They wanted scalability at pretty much any cost because they needed to build bigger and bigger services and continue scaling as they knew more and more users would be coming online over time. So these NoSQL systems had to give up a lot of things in order to get the scalability that they were after. They gave up the relational model, obviously. That's why they're called NoSQL, which is kind of a silly way to define a class of systems due to what they're lacking, but they're called NoSQL databases. And they also gave up things like transactions and joins and indexes for the most part. They usually didn't offer the same sorts of consistency of data that programmers were used to with SQL systems. And so, whereas Ted Codd in the 70s took complexity out of users' applications and brought it into the database to make life easier for developers, NoSQL systems did the reverse. So they took the complexity that had been built into the database to make life easier for developers and just pushed it back out into the applications saying, like, we can't handle this anymore. You're going to have to deal with this. You're going to have to work around the database's insufficient capabilities. And so now we're in the 2010s, and there's this new class of systems coming around, sometimes called NewSQL, or you can call it distributed SQL. Some people call them Elastic SQL, whatever the heck you want to call them. They're SQL databases that run on multiple machines. And why are these being built? I think it should be fairly clear at this point based on the history, but without NoSQL or without distributed SQL databases, you have to make a choice when you're starting a new product. Are you going to pick a SQL database and limit your future scalability? Or are you going to pick a NoSQL database and take on an extra development burden to work around the lack of a solid foundation to build on? Because the NoSQL systems don't have transactions and indexes and consistency in general. And there have been a lot of really successful services built on top of NoSQL databases, right? So they're clearly not completely useless. Tons of great services have been built on top of them. But it's a lot harder. And so Google, who published a paper about their distributed SQL database, which is called Spanner, back in 2012, put in this choice quote about why they thought it was worth it to build this system and to have most of their services switch over to using it. And they think it's more worthwhile to have their developers occasionally deal with performance problems than to always have to deal with the lack of transactions. It saves Google money in the long run to do this, because it saves their developers time and energy. And so that's why these systems are being built, because we want to try to eliminate that trade-off that was inherent in picking a database 5 to 10 years ago. So there's a whole class of these systems appearing that are distributed databases providing full SQL semantics, where you can go and talk to any of the machines in the cluster as if they're an individual node, but they'll do all the coordination under the covers to work together as a distributed system to process your queries. And so we're attempting to combine the best of both worlds. And these are usually built as entirely new systems, because to build this functionality into a previous database, you'd basically have to rip out the guts and put in entirely new guts, like an entirely new engine. And at that point, it's almost like building a new system anyways. So the two primary systems I'm going to be referencing a lot today, just because I'm most familiar with them, are Google's Spanner, which was published back in 2012 and had another paper published earlier this year detailing how it's changed in the years since. And then CockroachDB, which is because I work on it on a daily basis, and all the information is publicly available out there on the internet due to it being open source. So that's why these systems are being built. But there's still the question of how. So what makes them different? Why couldn't they have been built 20 years ago? And how are they getting this different set of trade-offs? So we're going to specifically focus on, as I mentioned earlier, how that data is distributed, how remote copies of the same data are kept in sync in a way that keeps it consistent, and how transactions work in the distributed setting. And for each of these points, I'm going to specifically compare all the different types of databases. So how SQL databases do things, how NoSQL databases do things, and how these new SQL or distributed SQL systems do things. As a brief disclaimer, there are a ton of databases out there that work in different ways. So there's a lot of SQL databases, there's a lot of NoSQL databases. I can't cover every little exception to every rule. I'll do my best to speak in generalizations that are as true as possible and point out exceptions where there are some, but there are too many systems for me to know all of them, let alone to point out all the differences today. And as I said, I'm going to be focusing mostly on Spanner and Cockroach as representative of new SQL systems, because they are fairly representative, but there are some slightly different designs out there for these new SQL systems as well. So let's dive into data distribution. All the data distribution means is just this question of how we're distributing data amongst the cluster. And for SQL databases, there's not a whole lot to talk about, because they're designed to run on a single machine, right? So all the data is on your one server. And you might have backups somewhere. You might have secondary replicas that are getting copies of the data in a streaming fashion. But all the data is on one machine, or all the data is copied onto a couple machines. There is this option, as I mentioned, to manually shard data across multiple instances of a database. But that's not the database software doing anything. That's still just the database storing all of its data on one machine, and the human who's managing the system spreading the data across multiple machines manually. So SQL doesn't really do data distribution. NoSQL and new SQL systems have to, though, because they're running with this core assumption that all your data is not going to fit on one machine. So you can't do things the SQL way. So there's this core assumption that means you're going to have to break up your data in some way and divide it up amongst all the machines in your cluster. So NoSQL really pioneered some of these techniques, and NewSQL has effectively just learned from them, saying, NoSQL did this well. We have no reason to change it. Let's keep doing things in a similar way. And so you have to answer, for all these systems, how you divide up the data into chunks, and then once you've divided it up, how do you find where those chunks are located within the cluster? Because it's no use to have your data broken up and spread out if you don't know where each piece of data actually is at any given time. There are two primary approaches to doing this, which we'll take a look at individually, hashing and order preserving. So this hashing approach to data distribution just means that you're going to pick a hash function, maybe multiple hash functions, and you run these hash functions on the keys, assuming it's like a key value system. So you run the hash function on the key, it spits out a result, and you deterministically map that result onto one of the machines in the cluster. Maybe just by doing a modulus on the number of machines or something along those lines. And this makes it super easy to find any piece of data, because all you need to do is run a function on this key, and you know exactly which machine or which machines it's going to be located on. So reads and writes can find the given machine they want to talk to really quickly. The problem here that makes this prohibitive for new SQL databases is that you can't do range scans, because hash functions don't maintain ordering of your data. So if you wanted to scan over all the keys from A to B, you can't do that efficiently in a system that's dividing up the data based on a hash function. So this approach is used in databases like Amazon's DynamoDB or in Cassandra by default, but it's not used in any new SQL databases as far as I'm aware, because SQL databases really rely on having ordered indexes in order to access data efficiently. So some other NoSQL systems like Bigtable and HBase, as well as most new SQL systems I know of, use what's known as an order preserving approach. And this approach means that you put all your data, lay it out from A to Z, or from the beginning of the alphabet to the end of the alphabet in alphabetical order, and just split it up into chunks by picking arbitrary dividing lines that give you nicely sized chunks in the middle. So you might have a chunk from the beginning of the alphabet through A, from A through F, from F through Q, and so on. And you just distribute these chunks evenly across all the nodes in the cluster. This is really good for range scans, of course, because we're keeping the data in order. All the data between A and B is in one place. You might have to talk to multiple nodes if you're scanning over a very large range, but the data is all going to be all in order for you. The downside of this, though, is that you no longer have this deterministic function from a given key to where that key is located. So you have to add on some kind of range indexing structure on top of your actual data to track which ranges exist in the cluster and where they're located at any given time. So what that looks like in practice is that you divide your data up into what we're going to call ranges of data. So you have a range from the beginning of the key space through lemon, from lemon through peach, and so on, that each just holds the keys and values that fall into that range of data. You also add on this range index on top, as I mentioned, and that's just going to track which ranges exist and where they're located. So anytime a query comes in, say you want to read the key mango, you go up to the top of the range index and ask which range does mango fit in. In this case, it's going to be the middle one, and that range index will tell you which machines that middle range is located on. So you can then just go send a request to that machine for that key. And it might seem like this is going to add a lot of overhead to all your requests, but in practice, these ranges don't move often or don't change often, so they can be really easily cached on all the machines, so that you don't have to do this extra lookup most of the time. And finally, you can do a range scan very easily as well, as I mentioned. You just look up where the start key is, you look up where the end key is, and read all the ranges that contain any of the data between those points. The last thing you have to ask about this approach, though, is when do you split up the data? Because you can do a split pretty easily, right, by just picking a point in the middle of an existing range and dividing it in two. So you could divide up that last range, from P to the end of the alphabet, and split it into two if you get a few more keys added. But you have to decide when to do this. So you could wait until the data got too big to fit on a single machine, or maybe you'd do it sooner. In practice, most databases do this when it gets to be about 64 megabytes or 128 megabytes, somewhere on the order of 100 megabytes of scale. And there's a trade-off here, because if you let your ranges get too big, then moving them between machines is quite slow. So if you need to quickly move them to recover data from a node that crashed or to rebalance how much data is on each machine, it's tough to do that with ranges that are really big. But if you make your ranges really small, then your range index at the top gets to be huge. Having millions or billions of these ranges adds an overhead into the indexing and the caching of that index. And so you don't want to have tons of them either. And because this is a distributed system, you have to assume that failures are going to happen from time to time. So you might have, or you have to have multiple copies of your data such that if any given one is on a machine that fails, you'll still have other copies of it available somewhere. And so usually this will be some number that's 3 or greater, might be user configurable. You're going to spread these around the nodes in your cluster, and you have to have some kind of control process that's doing rebalancing. Because what if a new node comes up into your cluster? An administrator adds a new machine to your data center. You don't want it to just be empty. You have to proactively move data onto it. And so this control system could live outside the cluster. It could live inside the database software itself. It doesn't make a huge difference other than in terms of how you operate it. But it needs to detect when there's this imbalance of data. So here, nodes 1 through 3 have way more data than node 4 does, so it makes sense to move some copies of ranges over onto node 4. So you'll move the copy of range 3 over there, and node 3 can just wipe that off its disk. It doesn't need to have it anymore. So you can keep doing this until the cluster gets approximately balanced. And you can do this both for the size of the data, the number of ranges in the cluster, or even the amount of load. So if some ranges are hotter than others and receive way more QPS, you could split them up into 2 and spread those out onto different machines in order to balance the QPS on each machine in your cluster, which can be important in practice. There's also the opposite case you have to deal with. So if a machine fails, you're running with fewer copies of data than you want, right? So you have to up-replicate these things, create new copies of them, so that you get back to the desired amount of replicas at all times whenever possible. So if node 2 fails here, we need to make a new copy of both of the ranges that it had on it. And then if the node never comes back, we'll still be OK and have enough copies. So that's how data gets distributed around these clusters, both in NoSQL systems and in these new distributed SQL systems. But once you do that, as soon as you have multiple copies of data in a distributed system, you really need to ask yourself, how are you keeping them in sync? Or how are you dealing with conflicts where one copy says one thing and one copy says another thing? Because it's bound to happen. Network requests will be lost, a machine will be down and might not be up to date, and you need to have some way of deciding which copy is correct at any given time. And so SQL databases, since they store all their data on one machine, don't really have to deal with this unless they're running some form of primary, secondary replication. But that is pretty common these days. Because if you have cold backups, you don't really expect them to be kept up to date all the time. But if you're running primary, secondary replication, there might be an expectation that your secondaries are up to date. Because the way primary, secondary replication works is just that you have one copy of your database that's considered the primary, where you send all of your writes, and oftentimes all of your reads. And the primary will just take each write it to its own disk, and then at some point send those writes off to the secondaries so that they can have the same copies of the data. And in theory, it's a very simple concept, right? The primary gets a write, it writes it to its disk, and it passes it along to the secondary or the multiple secondaries. In practice, there is a bit more complication. There are edge cases where you're going to lose data or where you're going to be reading stale data. And it's tough to really manage this as an operator. You have to choose between asynchronous or synchronous replication, where asynchronous just means the primary will write a write to disk and acknowledge it to the client, and in the background, it'll start sending those writes off to secondaries. What that means is that the secondaries won't necessarily have all the data the primary has. If you have to do a failover, you could be losing recent writes. If you're doing reads on the secondary, you could be missing out on recent writes. If you do the opposite approach, what could be called synchronous replication, that would mean that you're waiting on the secondaries to write the data to disk before telling clients that their writes have succeeded. This is going to introduce extra network delay into all of your write requests. And it also introduces interesting questions like, what if the secondary fails, or what if the secondary gets slow? How long are you willing to wait on that secondary to respond to a request before you just give up on it? And either way you do this, failover is really tough to get right, because you have a lot of clients in your data center presumably talking to this database, and they need to know which one to talk to at any given time. So it's tough to fail them all over without some straggling requests potentially going to the wrong instance and leading to a sort of split brain. But moving on to NoSQL, NoSQL systems really do a whole ton of different things to keep track of their copies of data. And most of them are what's known as eventually consistent, which is kind of just a euphemism for not consistent. Most of these different solutions for maintaining copies of data can fail in weird ways, whether there are partitions or not. They could be dropping writes if two writes come in for the same keys around the same time. One of them is just going to clobber the other, and it's non-deterministic. They could be serving up stale reads. So if you do a read at an inopportune time, you might be getting an old piece of data. In some situations, you might get an uncommitted piece of data, something that was never really acknowledged to be committed. The only solution here that really can be called eventually consistent, in that if you wait long enough, the data will truly be consistent with nothing lost, is these conflict-free replicated data types. These are some really cool algorithms that have been talked about at past Strange Loops, so I'd recommend checking out those videos if you want to learn a little more. But they do, in fact, keep all your data consistent if you wait long enough, if you let all the data from the different machines eventually converge. But we don't have enough time to really drill into the details of how all these different things work. You could fill multiple really interesting talks just doing surveys of all the different mechanisms NoSQL databases use to keep their data in sync. Just know that typically, they really don't keep data consistent in any way. You could lose data, get old data, et cetera. Keeping copies in sync in NoSQL databases usually works about the same, in similar ways between all the systems, which is a pretty serious change from NoSQL. Most NewSQL databases, or distributed SQL databases, use what's known as a distributed consensus algorithm. And these consensus protocols have been very heavily researched. There's a lot of academic papers proposing different ones, proposing improvements and variations on the existing protocols. And they've been proven through formal methods to be correct, to keep your data consistent and reach agreement on all the writes in the system. The most famous of these protocols is Paxos. It was originally written about 30 years ago almost, but is notoriously hard to understand and hard to implement. So there aren't really many implementations of it. Google wrote a paper on how many years it took them to get one of these implementations into a usable, reliable, production-ready state. It's really not easy. Raft was a new protocol written about 5 years ago by a PhD student at Stanford that has really taken off because it was designed from the get-go to be correct, but much more understandable and easier to implement. So now you can go out on GitHub and find open source implementations of Raft, just already written for you that you can throw into your own system and use to get reliable replication of data. It's not necessarily easy to use, but it's available if you want to use it. And so this has made consistent systems much more possible, much easier to write than they were 10 or 20 years ago, because these protocols have become simpler, easier to write, and more widely available. But the way that these protocols typically work is that they have some odd number of machines in a cluster, so 3 or 5, maybe 7. And commit just happens when a majority of those have written the data to disk. There is more in the details that makes them always correct, but that's the high level. And so let's take a look at Raft in particular. Raft is what we use in CockroachDB. We share an open source implementation with the lock-oriented database etcd. And it's a pretty hardened implementation at this point. And Raft is based around leader election. So if you wanted to describe Raft in 3 sentences, you'd say you have a set of replicas that elect a leader. And that leader appends incoming commands to a sequential log and assigns an index to each command. And if you've been to past strange loops, you've probably seen talks on how sequential logs are these really powerful constructs in distributed systems. So you have these writes being appended to a sequential log, and then that log just gets replicated from the leader to the followers. And the commands are considered committed once a majority of the nodes in the system have written them to disk. So in this example, if a write comes in for the key cherry, the write has to go through the leader, because all proposals in Raft have to go through the current leader. So the leader will write it to its own disk in that sequential log and replicate it to the followers. As soon as either of those followers has written it to disk, we suddenly have it written to disk on a quorum of them, right? So we have 2 out of 3. At this point, the write is considered committed. Even if all the machines were to be suddenly turned off at this point, that write would have been persisted. And at this point, normally the follower will acknowledge it to the leader, and the leader can acknowledge the write to the client. So you do have to wait this one network hop before you can acknowledge writes, which is a bit different from those SQL databases that just have everything in one place. But notice here that you didn't have to wait on that 3rd replica to write it to disk. All that these algorithms require typically is a majority to be up to date. So if one node is running slow for some reason, or say it gets shut off for a few minutes, or it's on the other side of the country, you don't have to wait for it, which allows for some interesting configurations where you can deploy 2 replicas on the East Coast and 1 on the West Coast, and those 2 that are close together can operate and serve these writes really quickly because they don't need to wait for the one that's far away. But that's what happens when things go well, and of course you need to ask yourself, what happens when things don't go quite so well? That's always a question in distributed systems, because you're going to have failures, you're going to have partitions, you're going to have all sorts of problems. And so if we have the same example where a write comes in for the key cherry, and the leader dies before it's able to replicate it, by the definitions we've been given, that write has not been committed, because it's only on 1 hard drive, right? So those 2 followers are going to elect a new leader while that old one is down. So we have the new leader now. The 2nd replica has become the leader. And it doesn't have that key, because the 2 replicas that were followers didn't know about it. So they didn't know that the leader is supposed to have this key. So if a read then comes in for that same key, according to Raft, according to the consensus protocol, that key was never written. It's only on 1 disk, and the leader doesn't have it. So the leader is going to go to its followers and say, hey, do you have this key? No, I don't. The 1st replica will then have to be asked to remove it because it was never truly committed. And on a leader changeover, any uncommitted proposals just get dropped. And so at this point, the key is just returned as not found. And that's like a just surprisingly thorough overview of Raft. I mean, there are more details, of course, but it is a very understandable algorithm. I'd recommend reading the paper if you're interested in this kind of stuff. In practice, NoSQL databases like Cockroach and Spanner have to run one of these consensus groups for each range of data. So in that example from earlier, we had those 3 ranges and 3 or 4 nodes. We'd have to have 1 group for each of those ranges, so 3 consensus protocols running in the cluster. And in practice, we have way more than 3 ranges, right? Because we're restricting them to be about 64 megabytes. So if you have terabytes of data in your system, you could have hundreds of thousands of these ranges. So there are a lot of engineering complications that come into play in these systems. It's tough to scale to have this many ranges and to be able to handle member changes when you're moving them between nodes, to handle splitting them consistently, to deal with software upgrades where some nodes are running different versions of the software than others. But these are all engineering complications that can be dealt with through just hard, diligent work, assuming you have the solid foundation of research underneath you telling you that this replication is correct. And so finally, let's take a look at transactions. So we have consistently replicated data on a per range basis, but SQL databases allow transactions to touch any rows anywhere in the system. So you have to handle coordination between these ranges, between these consensus groups. And so these groups might be on different machines all throughout the cluster. And when we're talking about transactions, we're talking about good old school ACID transactions, where you can have any combination of reads and writes that touch any of the data in your system that are atomic, consistent, isolated, and durable. The two more interesting facets here, the two tougher ones to provide are being atomic and being isolated. Consistency is really just about checking user-defined constraints, like uniqueness constraints or foreign key relations and things like that. And durability is really just about synchronizing your writes to disk properly. But the hard parts, from an architecture perspective, are being atomic and being isolated. And so atomic means that all of the writes that are sent together as part of the same transaction either commit or none of them commit. You have to get all or nothing. And being isolated means that having concurrent transactions trying to operate on the same data in the system, that they can't interfere with each other. So it's as if they all have their own correct, consistent view of the database at all times. And there are multiple isolation levels, but we're just going to focus on serializability today, because that's the isolation level at which you don't get any anomalies, you don't get any incorrect data back out of your database. And the serializable level is required by the SQL standard to be truly compliant. So first, let's look at SQL databases. And a lot of SQL databases are proprietary, so I'm focusing specifically on Postgres here. The way that Postgres does atomicity is that all the mutations that are applied as part of a transaction, all of those writes, when they get written to disk, they're written with the transaction ID associated with them or attached to them. So if I write to the key cherry, it's going to have this little marker next to it saying it was written as part of transaction foo. And those writes aren't considered to be visible to reads necessarily, because they're still tagged with that marker. And transactions have to know which transactions have committed or not. When you do want to go ahead and commit the transaction, you have to write it to this commit log. And that's where the atomicity comes in. Because you can do a single write to a disk block in an atomic way. And so if we can do this single disk write to the commit log to mark that transaction as completed, then we have, in one fell swoop, committed every operation that happened as part of the transaction. And that one disk write will either fully succeed or fully fail. That's guaranteed by the disk. So that's how you get atomicity of all these writes spread out over the entire system to be committed all at once. You boil them down to just this one disk write. Isolation is provided in a couple different ways, which we'll look at individually. Read-write locks are the easiest way or the simplest way to provide isolation between transactions. This is how SQL databases did it for decades after their creation. And it's exactly what you would think. It's the same as using a read-write mutex in your own program. When you want to access a row, you take a read lock on it. When you want to write a row instead of read it, you have to take a write lock on it. And read and write locks exclude each other, right? Because that's how read-write mutexes work. And then you have to hold these locks until you commit, and release the locks once you've committed your transaction. So the database has to do some deadlock detection, but this is pretty simple to understand and pretty simple to implement as well. There are ways to reduce your isolation level by releasing locks earlier on in the transaction, but then you'll have potential anomalies appearing in the behavior the user sees. The other approach to doing isolation in SQL databases is what's known as multi-version concurrency control, or MVCC for short, because that's quite a mouthful. And what this is that anytime you write a row to disk, you store a timestamp along with it. And that timestamp represents the timestamp of the transaction that was writing it. And anytime you update the row, rather than overwriting the row on disk, you have to just write a new row next to the old one with a new timestamp. So you're not getting rid of the old data. And then anyone that wants to read a particular row has to get the most recently written version of that row from before the read zone timestamp. This has a few nice properties in that it allows access to historical data, because we're not deleting and overwriting the rows. You can run a query, as of 24 hours ago and get a consistent view of what the state of your system was then. This could help you track down things like bugs in your application that have started writing funny data to your database. You could pin down when the issue started happening. And the other big win is that it allows long-running read queries to not exclude other transactional workloads from happening, because you're not holding on to these write locks anymore. You're just running at an older timestamp and not blocking anything else from happening. So MVCC by itself doesn't really provide isolation. You have to have conflict detection on top of this in order to prevent transactions from doing things that they shouldn't. So you have to be able to tell when a transaction is trying to write or read to a key that something else has also been accessing recently. So it's a little tougher to implement. Postgres implemented a version of this, I think about a decade ago, that it uses for certain isolation levels now. And so NoSQL systems don't have a whole lot to talk about, because they, just as a rule, don't really offer transactions. The best thing you're going to get in most NoSQL systems is a single key transaction. So you might be able to do a read, modify, write loop on just a single key. But you won't be able to atomically commit multiple keys at the same time. Or write some keys on one part of the system, then do some reads, then write some keys somewhere else, and have that all happen as an atomic event. It's just something that they sacrificed in order to achieve scalability at the time. Because transactions imply coordination, and coordination is hard in distributed systems, right? So it was going to be a lot of engineering work for them to try to do this. And so this is kind of all I can really say about NoSQL transactions. Finally, distributed SQL has to support the same semantics as traditional SQL databases, because you can't replace a SQL database as a drop-in replacement unless you have the same semantics. So we need full ACID, we need serializable isolation, and that takes a bit of work in a distributed system. But we can learn a lot from how SQL databases do it. So we can provide atomicity in a similar way. All writes that come in as part of a transaction can be tagged with a transaction ID as usual. And we just have to have this transaction record somewhere in a consensus group. Because writes to a consensus group, a Raft group or a Paxos group, are atomic. They either do happen or they don't. So whereas a single node SQL database can use a single disk write to get atomicity, we can use a single consensus group write. So it just takes that flipping of the transaction status from in progress to committed to mark it as done and to mark all of the writes involved as done. And isolation can also be done somewhat similarly to single node databases. It's a bit harder due to the network latency involved and the fact that all the state isn't being held on one machine in the same memory space. But we can use similar approaches. I think most NoSQL systems that I'm aware of, at least, use some form of MVCC. Spanner uses a combination of MVCC with two-phase commit and two-phase locking. They have to rely a lot on their very special hardware clocks that are in the Google data centers these days. CockroachDB uses pure MVCC with conflict detection. And it has to use a combination of hardware and software clocks to make this work reliably over widely distributed networks. So if you do have replicas on both coasts of the US, for example. But let's take a look at this MVCC and conflict detection approach to transactions. So you'll start by beginning a transaction and putting a key to the database. And that key will be in some range. And for convenience, in Cockroach at least, we put the record for that transaction tracking its status in the same range as that first write, so that they're co-located if the entire transaction happens to be happening in just that one range. So you'll start the transaction, and you'll write the key. And notice that the key is tagged with the transaction number, which we're just using 1 in this case. And that's to indicate that it might not be committed yet. If some other transaction comes along and wants to read the key cherry, it's going to have to check the transaction status for that transaction to be aware of whether or not it should be returning that key. The transaction can go off and write keys in other ranges of the system, other tables of the SQL system, and so on. So it could write Mango in another range. And then when it's done, it just has to go and do a single consensus write to flip the status of the transaction record. So it's going to mark it as being committed. And at this point, the transaction is done. Any new transaction that comes along and reads those keys will know to just go check the status of the transaction, and it will see that it's committed. That does add some extra work to the reads, though. And so after a transaction finishes, it goes and proactively cleans up those transaction ID pointers so that anything that comes along later to do a read doesn't have to go do that lookup. And once we've cleaned up the pointers, we can also just get rid of the transaction record because it's not needed anymore. But again, anytime you're talking about one of these distributed systems, you have to ask about what happens when things fail or when things conflict, when things don't go wrong in general. So let's take a look at one particular type of conflict. That's going to be a write conflict. So the transaction will start out in the same way. It'll write a key and put a transaction record for that transaction into the same range. But then another transaction is going to come along and try to write to the same key. And so in this case, the state to detect that a conflict has happened is on the range itself. So the machine that's currently responsible for serving queries for that range knows that something else has written to that key recently. So we have a conflict here, but we've also detected it. And so there are multiple ways to try to handle this. You can make the transaction wait on the first one that's already running, or you could do an abort of one of the two transactions and force them to restart. And so assuming we're going with the abort method, you have to pick one of the two to abort. And so this can be done with a priority scheme. So transactions can have a priority assigned to them when they start. It could be user assigned. It can be randomly generated. And you make the higher priority transaction win, for example, so that it's less likely to be aborted by a lower priority one. In this case, transaction 2 has to check whether the transaction 1 is done, though, because maybe transaction 1 is already done and transaction 2 doesn't have to worry about it. In this case, it's not, though. So transaction 2 is going to decide to push or abort transaction 1. Push would just mean to make it have to start over at a higher timestamp. So transaction 2 has aborted the conflicting transaction. It can update the write to its own key, where intent just means the transaction ID tagged on it, and then commit. So at this point, transaction 2 is done, and transaction 1 is going to have to restart. It might be able to do this restart internally to the database, or it might have to send that abort message, the abort error, out to the client for the client to retry. So that's a quick overview of how these conflicts work, of how these systems work. More details can be found on the Cockroach Labs blog, in the Spanner academic papers, other descriptions of these systems online, because this description had to omit things like the MVCC itself and other types of conflicts. So to summarize, anytime you're looking at a new system, whether it's a database or some other kinds of thing, you should try to understand why it's being created. How does it fit into the historical context of that type of system? Why is it being built now? Why couldn't it have been built a while ago, or why wasn't it built a while ago? And try to get a better sense for what trade-offs are involved in picking a system. So we've done that for these distributed SQL databases. We've also tried to understand how they work in comparison to past databases. So how they distribute data, which they do in a very similar way to these NoSQL systems. How they replicate that data in a consistent way, which is done in a new way, different from SQL or from NoSQL. It's notably not new to academia, though. I mean, these consensus protocols have been around for decades. So it's taking this existing work from academia and bringing it into a system in a new, novel way. And then how transactions work, which has been done by learning a lot from how SQL databases work and then just applying some engineering elbow grease to make it work in a distributed setting. So thank you a ton for coming out and listening today. I'll be around for questions afterwards. I'd recommend, if you are interested in this, there are a lot of great academic papers out there on these topics. You can check stuff out on the Cockroach Labs blog or on our GitHub repository, since it is open source with all of our design docs. But thank you for coming.